Here is something interesting which is not taught in the schools. In general, free light has 137 times the wavelength lambda of bound light for the same energy E. Have you heard that before? I don't think so. Let's see how it works. For bound light in atoms, you might have two electrons repelling one another, or a proton, P+, and an electron attracting one another over a distance lambda. Then the electrical energy would just be E squared over 2r or 2 lambda. And then using the fine structure constant, we get E squared equals 2 over hc divided by 137. And then that gives you a lambda for the interaction of 1 divided by 137 times hc over E. All very well known. Now for free light in space, we have a much longer wavelength at the same energy, lambda. And you can work out quite easily from the well-known formula E equals hc over lambda, that lambda equals 1 times hc over E. So for the bound light, hc equals 1 divided by 37 times hc over E. And for the free light, the wavelength is much longer, lambda equals 1 times hc over E. Let's look next at the 1s orbital of a hydrogen atom as a further example. For bound electrical light inside the atoms, we see a wavelength for the bound light, 4 pi r, which is 2 turns, 6.7 times 10 to the minus 10 meters, is well known. And then the free light, which is emitted, lambda free, 920 times 10 to the minus 10 meters. That's 137 times longer. Therefore, for the same energy E, the lambda B of the bound light is 137 times smaller than the lambda F of the free light. If we continue to give specific examples for hydrogen 2s or 3s atomic orbitals, we see for 2s, the wavelength of the bound light is 16 pi r, or 26.7 times 10 to the minus 10 meters. The wavelength of the free light is 3650 times 10 to the minus 10 meters, which is 137 times longer. For 3s, the wavelength of the bound light is 36 pi r, 60.3 times 10 to the minus 10 meters. The wavelength of the free light is 8280 times 10 to the minus 10, which is 137 times longer. So always, in general, lambda free equals 137 times lambda bound. Let's consider next what might be happening here in terms of quantum physics. Now first we're going to look at bound electrical light. And here we have a proton and electron attracting one another over a distance of 4 pi r, like in the 1s orbital, over a time of 3.1 times 10 to the minus 16 seconds. And during that interaction, we have all sorts of electrical exchanges, each of amplitude 137 back and forth between the proton and electron, left, right, The one-way amplitude is 1 over 137. The two-way probability is 1 over 137 squared, and that's very well known. Finally, let us visualize what's happening here in terms of the free emitted light that comes out of the atom. We still have the same time, 3.1 times 10 to the minus 16 seconds. We have time going that way, xy space going that way. Now the wavelength is 137 times longer. Lambda equals 4 pi times 137. And we can visualize that inside the atom we have these little short fragments, like I showed earlier, little double fragments, which are of wavelength 1. And then when they come out, they get longer at wavelength 137, like this big long polymer of fragments, to make a complete turn of one wave. So my hypothesis to explain this is perhaps a series of bound short fragments, 1, may polymerize through space and time to form a long periodic turn 137 for free light in space after it's emitted. So it's these little things coming together when they leave the atom and they form this big long light particle that travels through space. The implication is that light particle might have 137 parts of those little ones for each periodic turn.